Hey everyone, my name is Junichi, and I'm really happy to here today with my collaborator Doga to present our work on FoldTronics. This is a collaboration between MIT CSEL and the University of Tokyo. Today, 3D printers can already print passive objects such as decorative base you can see here on the left side, or a mechanical gear and crank mechanism you can see here on the right side. However, 3D printing active objects with circuit and electronic remain challenging. Conductive filament has too high of resistance to work for anything beyond simple LED circuits, while 3D printing with silver ink turned out to be very difficult. The Voxel Edge 3D printer, the most promising platform in the space of printing with silver ink, for instance, has recently been discontinued. Since 3D printing is not yet at the level to make fully functional objects, researchers have looked into alternative fabrication methods. One method, for instance, involving dipping the object into bath with silver traces, as you can see here on the left side. As you dip the object with silver traces adhere to the object's 3D surface. Another method is to use vacuum forming. Users start with a 2D sheet on which they press on the circuit. That 2D sheet is then formed into the 3-dimensional shape by applying vacuum. Finally, researchers have also suggested to use folding to make 3D objects with circuits. As you can see here, users again start with 2D sheet on which they print the circuit and then fold it into its 3D shape. While all of these methods made a big step forward in allowing users to create 3D objects with electronics, there is one limitation with all of them. The circuit and electronics are only placed on the outside of the object. But as you have noticed, when you look at your mobile phone, your laptop, and your electronic devices, electronics are actually rarely on the outside of the object. They are typically embedded on the inside. So our goal with this project was to develop a fabrication method to enable electronics inside the 3D object. So here's how we do it. While investigating different potential solutions, we found the foldable honeycomb structure actually offer a unique set of properties to solve our problem. Similar to existing method, I just show you honeycomb structure start out with a 2D sheet, which make it easy to place circuit and electric components. However, it contrasts other method. Once you fold up honeycomb structure, it forms a volumetric cell inside 3D geometry. This is a fantasy for our use case, since this allows us to position the electronic precisely inside 3D geometry whenever they are needed for instance, sensing or actuation. Here is a short preview of what this looks like once we have the electric applied to the seat and fold it up. On the right side, you can see the several sensors are inside the different cells, and we will tell you more about this in the second.
We already told you about the main motivation behind FoldTronics, which is to develop a fabrication method to enable electronics inside 3D objects. But before I dive into technical details, let me show you some cool examples we built using this technique. So here, for instance, for a chemistry workbench, we developed this test tube case that can measure the liquid level of each tube. As you can see, as I insert the tube, which is only partially filled, only 2 bars are shown on the phone screen that you see on the left. Now I insert the full tube, and the phone displays a full indicator with 3 bars. To enable this, each cell contains 3 infrared reflectance sensors inside. As the tube gets inserted, the reflectance of each sensor changes depending on the liquid level of the tube. If you look closely in this image, you can not only see the IR reflectance sensors inside the cells, but you can also see the routing of the wires that connect the sensors to the microcontroller. Another example we built is the smartwatch that can transform from a 2D to a 3D display. Here is the 2D display. And now I have the 3D display. To enable this, we added 18 LEDs inside the different cells of the 3D geometry with the right spacing. Here's our final example. This game controller has touch buttons inside to detect when I want to shoot in this arcade game. In addition, I can also transform the game controller into a different shape, such as from a small weapon to a large weapon, by expanding it or compressing it. This interaction is enabled by an expansion sensor that we embedded inside, which is basically also just a contact button. Now that I have shown you several sample objects, let me tell you more about how we actually make them. Our FoldTronics design and fabrication pipeline consists of 3 steps: device design, wiring, fabrication, and assembly. Let me give you a short preview of each step. Users start by loading their 3D model and converting it into a honeycomb structure using our custom conversion tool. Here you see the example objects I showed earlier being converted: the smartwatch, the test tube case, and the game controller. In the second step, users wire up their electronic components using a custom Eagle plugin we developed, and I'm going to tell you more about it in a minute. Here you see the wiring being done for the smartwatch. In the final step, users use our new fabrication pipeline to create the physical object. We only use low-cost materials like plastic sheets and conductive tapes, and cut them using an inexpensive cutting plotter. So now that you have seen each step briefly, let me explain how they work in more detail. Using the example of the simple circuit with an LED that you see in the picture. Here you see the circuit unfolded. It has an LED, a battery connector to add a battery for powering the circuit, and a cross-cell connector that I will tell you more about later. Okay, let's start with the first step. We already created the 3D model that will hold the LED circuit. Next, we click the Convert button to transform it into a honeycomb structure. Next, we add the LED. For this, we select it from the electronic components panel on the right-hand side that contains different electronic components. As you can see here, when we drag the LED onto the honeycomb, it automatically snaps to the next available cell to make the design process easier. Similar to how we place the LED, we add the other components, the battery connector and the cross-cell connector, and then hit the export button. On export, the 3D editor generates all the different layers necessary for the fabrication process. However, if you take a closer look at the wiring layer, you will actually notice that it's missing the wires. While the 3D editor knows where the electronic components will be placed, it doesn't know how to route the traces through the structure. Thus, we have to do one more thing before fabrication: wiring the components using our custom Eagle plugin. Our custom Eagle plugin uses Eagle's auto-wiring feature, taking into account our specific folding constraints based on the honeycomb structure. Once the auto-wiring is completed, we can export the file. And now that we have replaced the missing wires with the correct file, we are ready to fabricate the object. As you've seen before, our fabrication stack consists of 4 layers. We start by cutting and perforating a plastic sheet which makes up the honeycomb's base. Next, we put conductive tape on the perforated sheet and cut it to generate the wiring. Folding the sheet as is would result in short circuits since the copper traces may touch each other. To prevent this, we add an insulating layer of regular tape on top, and we cut it again. If you folded the structure right now, it wouldn't hold together. To make the honeycomb cells stick, we use double-sided tape as the last layer. Then we solder the components onto the wires. Here we attach the LED. Once we're done, all we have to do is to fold the sheet and power up the circuit. I just showed you the 3 steps that make up the pipeline. And I showed you these steps using the example of constructing this simple circuit so you would be able to follow along. However, our fabrication pipeline works for complex geometries as well, such as the smartwatch or the test tube holder that we showed previously.
Now, let me show you more details on how we implemented the custom 3D editor and the Eagle plugin. We want to talk about how we actually generate these layers, honeycomb, wiring, insulation, and glue surface from the 3D model. First, we explain how do we convert a 3D model into a honeycomb shape to create first layer for the fabrication pipeline. To better understand this, let me show you first how honeycomb structures are folded. Each column on honeycomb cell consists of segments called valleys and mountains that are folded in opposite directions, which gives a strip each characteristic shape. To create both sides of column, we need to duplicate the pattern and additionally place cut to form the follow cells. Finally, to create more columns, we can simply keep duplicating the patterns as many times as we need it. So here is how this works in software. First, we split the model into 2D planes to create the columns for the honeycombs. Next, we create segments on each plane so that we can fold the seats. Once folded, the strip makes up half a honeycomb cell as shown. Finally, we duplicate the 2D plane so that we get the whole structure when folded as shown on the right. We then project the structure onto the 2D sheet, which gives us our first layer, the base of the honeycomb that is fabricated with the plastic sheet. To generate the second layer, the wiring, we first have to figure out where the electronic components have to be placed on the 2D sheet. Since we already know where 3D cell goes where onto the 2D sheet, we can simply correlate into which 2D cell segment the electronic component should go. Next, we can use the sheet with the electronic component placement marked and import it into Eagle for wiring. Our Eagle plugin first generates a circuit board based on the size of the honeycomb pattern. Next, it converts a colored square into matching electronic components based on the lookup table. Using the generated board and electric component, we then use Eagle's standard auto routing function to generate the wiring layout. The insulating layer is simple in that it covers all cells except those that have an electronic component. Similarly, the last layer are made of double-sided tape to hold the honeycomb together based on the dimensions of the base sheet. I explained about the implementation and how we generate these layers using 3D editor and Eagle. If you are interested in more details, please see the paper.
We showed you the basic working principle of FoldTronics. Now let me briefly talk about some extra features we developed. When routing wires, there's only limited space available on a cell side. For instance, here, the maximum number of wires we can fit is 4. To increase the number of wires, we created the cross-cell connector you see on the right-hand side, which makes use of the fact that when the honeycomb is folded, both sides will touch each other. By using this cross-cell connector, we can double the number of wires to a total of 8. This is what it looks like when fabricated. To make the cross-cell connector stick, we use double-sided conductive tape. So far, we only used one-sided circuits. However, if we apply the same stack of layers on the bottom of the sheet as well, we can make double-sided circuits too. You can see an example of this on the right-hand side, where there are wires both on the back and the front of the sheet. To connect the front and the back, we also insert an eyelet. Before we conclude, I'd like to mention some limitations of FoldTronics. First, fabrication of objects requires manual assembly. Second, the honeycomb cell size must be large enough so that components fit inside. Third, the copper wires may not be robust enough if they are thinner than 1 millimeter.
Okay, let me sum this up for you. In this paper, we presented a new fabrication method to enable electronics inside 3D objects. We demonstrated how our technique can create a variety of 3D objects with integrating functions, and showed how our design tool helps users to create these objects by helping with all steps from converting the 3D model into the honeycomb structure, wiring electronics, and by keeping the fabrication process simple. For future work, we have already started investigating the use of inkjet printed silver inks used in flexible PCBs to make the object more robust to folding. But really what makes us most excited about our project is that at its core, it is one step toward our larger mission of increasing the range of interactive 3D objects we can make today. Thank you very much for your attention, and please feel free to come our demo at interactivity session. Thank you.